Okay, so topic is RSocket, which is a new application-level networking protocol. Well, not new, it's been around for a while, but new in terms of concept. Just a show of hands, how many people have heard of RSocket before? All right, and how many have actually used it? All right, well, we're hoping to change some of this today, hopefully, after today. So just very quickly, I'm Arsalan Farooq. I am the CEO at Netify. I am a bit of a serial entrepreneur, as well as I grew up at Oracle, so lots of history dealing with enterprise-class deployments and infrastructures. With me today is Robert. He's our Chief Innovation Officer, which is just kind of a big word for the smartest guy in the company. So we're going to be talking about it. I'll just very quickly just introduce the project, and then we'll let Robert talk about things that you guys are more interested in. So we're Netify, and RSocket is an open source protocol that was basically germinated some time back inside Netflix and other places. And right now we're working with Facebook, Alibaba, Pivotal, and other partners who are on board, and we are sort of using and promoting RSocket. And we're hoping that us together and with other incoming partners will be able to change the fact that few people have heard of RSocket. Hopefully more will have and will use. I should mention that Facebook, Pivotal, and Alibaba, they're all using RSocket internally. Pivotal's, for you Java developers, the Spring Framework 5.2 is coming up next month, and that has RSocket built in. So if you like to use Spring, you'll be able to get on RSocket immediately. What it is basically, it's an application level, layer 5, 6. Loosely speaking, I call it layer 7, but I know I'm wrong. It's got built-in reactive semantics, so back pressure, composable, flow control, all of that stuff is built into the protocol. You should be thinking, compare that to HTTP or other REST-type protocols you've heard, and we'll see how that works in a minute. It does have flow control built in, which basically means that you don't have to worry about things like retries and other things that you have to write in your glue logic when you write your applications. The network and the protocol will take care of it for you. For those of us who are old enough and remember TCP/IP at a lower level, that had flow control built in, and that's why we never have to write a lot of the glue code that we have to write at application level. So going to RSocket will change that. Binary encoded, and it's message passing based, which Robert will talk about why that's important, and allows you to do, to get asynchrony in your applications very, very quickly. So let's, I think that's kind of enough for me, and I'll hand it over to Robert. Your mic's working?
Hello? Yeah. Hi. So I want to talk about what's needed for high performance microservice networking. So when I thought about this talk, I came up with a list of things that I think are important for building performant applications. So firstly, we need temporal and spatial decoupling. Next, you should actually be sending binary across the network. You shouldn't be sending text encoding. And then finally, you need application flow control, because you want a consistent application. An application that isn't consistent, that has bad tail latency in a distributed system, is actually very slow. So let's look at loose coupling. So when I think about loose coupling, I think about spatial and temporal decoupling. And so what spatial decoupling is a message sender should not directly call a destination. Instead, it should pass a message to somebody else through a stream or a channel. And then temporal coupling is that when you call something, the thing that you call should not block the execution. So you can think of that as like non-blocking code. And this will let you more efficiently use your resources. RSocket is loosely coupled because it uses asynchronous message passing. And when we talk about message passing, something that comes up a lot is, what's the difference between an event-driven architecture and a message-driven or message passing architecture? So I created a quick list of things here. But the really big thing to take away from this is that in a message-driven architecture, you send messages to a destination. And in an event-driven architecture, what you do is you actually listen to events emitted from an entity. And so one way to think about this is message passing would be your boss tells you to go fill your timesheet out, right? But an event-driven architecture would be more like your boss actually sends an email to everybody and says, hey, fill out your timesheet. So let's take a look at what that looks like. So on one side, you have something that emits events. In the middle, you have some kind of queue usually. And on the other side, you have things that are listening for events, right? And so it's all good. You begin to emit events. Things go in the queue. Many people are familiar with this. And you begin to just pull stuff off and process it, right? And the messages that are sent, or sorry, the events that are sent aren't actually correlated to anybody. So anyone can go ahead and just pull that off. And you can't actually tell, where the message originated and where it came from, right? They just go into the queue and people go ahead and process this. And this is generally okay, except it ends up leading to a few problems. And some of those problems are, how do you actually send a response back to someone, or send a message back to a particular person emitting events? It's very difficult to do this, right? You can't do this because you generally don't actually know where the event came from, right? And besides just sending an event, you might actually want to send an exception, right? So what could happen is you might have a device that's emitting a bunch of exceptions, right? Emitting payloads that are causing exceptions. So those payloads go into the queue, and you can't actually tell which device is doing that because there's no correlation between the thing emitting the payloads and the processing causing the exception, right? And then finally, back pressure is a lot harder to deal with in this kind of environment. So you can only really do back pressure around a queue right now, right? So you can't actually tell one of these things emitting events to slow down and stop sending you events, right? Because there's no signal. You can't actually say, hey, you're sending things too fast for me to process, right? And so what can happen is you can have one bad device or one bad deployment that actually goes ahead and blows up your queue for everybody else, right? Because you can't say, hey, stop sending me stuff. Actually, this is kind of funny at Nike. When I worked on the fuel ban, we called this the Mark Parker problem. So Mark Parker is the CEO of Nike, and every time we gave him a fuel ban, inevitably he would have a bug, and then like buried halfway through the queue or his device, he'd end up actually breaking the fuel ban, so he'd have executive tech support come to fix it. So I'm very familiar with this thing, and it ends up causing a lot of issues. So let's take a look at how this would work with message passing. So in message passing, instead, you have different destinations, right? And what the destinations do is they begin to send messages to each other over, distinct streams, right? So destination 6 sends a message to destination 1, right? And then conceptually, unlike event-driven architectures, something that receives a message can go ahead and pass it on to somebody else, right? So in this case, destination 3 gets a message, it can send it off to another place, right? And then more importantly, you can actually go ahead and send messages back and forth between different destinations, right? And so you can use this for request reply, or you can also begin to use this for other things. Signal, maybe you need to slow down or send an exception for someone to handle, right? So let's take a look at the way that RSocket uses message passing in the protocol. So RSocket has a bunch of different interaction models, and there's some really great talks about it. I won't go over that. But one of the interaction models it has is the ability to create a bidirectional channel between two different destinations. And the way that it starts doing that is it goes ahead and sends a message over from destination 2 to 1 and says, hey, I want to do a bidirectional channel, right? And then RSocket has this built-in idea of back pressure. So even though destination 2 sent a message over, nothing will be emitted until the person goes ahead and asks for it. So what happens is it sends a message and says, hey, go ahead and send me 3 different payloads, right? And so it begins to go emit the different payloads at the rate it cares about. And then importantly, too, it doesn't actually have to emit them at any set rate. So it can choose not to emit it as well. So if it ends up chewing up too much resources, it can just stop. Anyway, it emits these payloads. And then when it gets to the 3rd payload, it stops sending anything else, right? So if I talked about the previous example in an event-driven architecture where you go ahead and have this rogue program that's emitting data, it can't actually happen in this, because what will happen is you'll emit the 3 pieces of data and then it will just stop. It won't send any more data, and you won't actually have that situation where one bad actor can go ahead and just take up all your system resources. And then because this is a bidirectional channel, destination 1 can go ahead and say, hey, go ahead and send me data back as well. But 2 doesn't have to do that. Instead, it can go ahead and send other messages, which is like, go ahead and complete this transaction. I want to stop doing it. And then the thing that's actually the most useful in this architecture is, let's say the third payload's actually causing you issues, right? Well, when destination 2 gets the third payload in an event-driven architecture, there's no way to actually go ahead and really correlate that back to the area where it's emitted. But in our socket, when it gets it, it goes ahead and basically sends an exception frame back to the caller so that you can very easily see that, like, oh, I sent this message to this guy, and then the message comes back. So this is how our socket is loosely coupled. So it is spatially decoupled because it sends binary messages over a dedicated stream, and it is temporally decoupled because all of its APIs are non-blocking. So what kind of messages does our socket send between the different destinations? Well, our socket sends binary payloads between the different destinations, and it accesses those payloads and processes them using a flyweight pattern, which is very efficient. Basically, it doesn't have to allocate objects to do this, and it allows you to do things like zero copy in a very efficient manner. And it does this across languages. So the different implementations of our socket, whether it's in JavaScript, Java, C++, all use this same pattern so they don't create extra garbage. Let's take a look at how our socket actually does this processing. And this is something like when you move to threaded code and multi-threaded applications that you can get wrong really easily and actually create a situation where it looks like you might be CPU bound, but you're actually not. So I have a really simple application that's just doing some work. Basically, pretty easy to see. Basically, it's going to go ahead and count. And what this conceptually looks like is there's one thread going ahead calling this simple little program and running it, right? And it turns out this is incredibly fast. Like on my laptop, this took less than a microsecond to run, right? Like basically in a microsecond, you can count to 2 billion on a laptop, right? But of course, we need to like make this faster, and everyone knows the best way to do that is to just go ahead and add as many threads as possible. We get like a 128 core box. We're going to just add like 128 threads to this guy, and we are going to totally blow this out of the water, right? And not only that, we're going to use atomics and just make the best program ever. And so, like, how long do you guys think this took to run? Does anyone have a guess? Anyone know? No clue. So this is kind of what it looks like. Everyone's helping you out counting, right? Everyone's going to lend a hand and add to this. But when I ran this, guess what happened? I didn't wait for it to finish. It let it run for like 10 minutes on my laptop, and it never completed. In fact, I didn't actually think it was working, so I changed the target of 2 billion to like 2,000. It still took 30 milliseconds, 40 milliseconds to actually run, right? And so basically what's happening is you're causing contention in the CPU, right? So not only are you not on your CPU cache, which is very fast, you're actually in slow main memory, right? And then you have all these people like going in at once trying to like go and help at it. And like the way I like to think about it is imagine you have like a 8-lane highway, right? And then at the end of the 8-lane highway, it all goes down into one road, and you're just trying to jam as much stuff through. And when you run this, you run something like this, you can actually go look at your task manager, and it looks like you're running at 800% CPU on my laptop. It looks like it's just churning through stuff, and I'm like, oh, I must be totally CPU bound, right? But you're not, because you saw the last application, it ended up like taking less than a microsecond, right? So what can we do? Well, this is something that happens a lot behind the scenes in RSocket and other reactive libraries. And what we want to do is we basically want to take our application and turn it into a bunch of single-threaded applications for you, right? And so what we end up doing is we end up controlling threads accessing the work we want to do with a shared variable. And then locally, we go ahead and cache it, right? So we end up doing the work, so it's all on the same CPU, so it's very fast. And then when we're done, we go ahead and we make it available to everybody, right? And so what this kind of ends up looking like is this. You basically have a bunch of little single-threaded programs that run, right? And there's way less contention. So when you go ahead and run this, it also ends up being pretty quick. It takes less than a millisecond to go through and churn through all this, right? And a nice side effect of this is the threads that aren't actually doing the work are free to go do other stuff, right? So they're like, oh, I want to do counting. Oh, I can't count. So they might go do some other application. And the way this actually ties back into message passing is, replace the silly little counter with, say, like a message queue or something, right? So everyone's pulling the message queue. One person wins. They get to drain the queue. The other people are free to go off and do other stuff. But no one actually wants to program like that all the time, and I can tell you it's pretty awful to deal with. It gets way more complicated. But thankfully, we have libraries available that abstract this away for you and end up actually basically doing the same thing under the scenes, right? So they end up going ahead and doing all that complicated work. So you end up getting the same result that happens as if you did this by hand. You get these basically little single-thread applications, and when you run that application, it ends up taking less than a millisecond as well, right? So to circle back to RSocket, how this connects together. So Reactive Streams abstracts away message passing for you, right? And the interesting thing about message passing is there's no difference in message passing between something that's on box or off box, right? Like for the caller. So if I call something, I don't necessarily have to have it be on the same box as I'm on, right? And what RSocket ended up doing is taking that abstraction and then creating a protocol that makes that work across the network, right? And the end result is you can basically take this reactive code that was there earlier and swap in RSocket without actually changing any of the calling code, right? As far as the person making the call is concerned, it's as if it's on box, right? Or just some asynchronous code that's running. So if we go back and look at the last little snippet of code we have here is the piece that goes off and does the counting is actually encapsulated in a Reactive Streams context, and we can go ahead and switch it with a really simple little request reply piece. And then if you go look, the person that's actually doing the calling isn't changed at all, right? As far as they're concerned, this could just be some threaded code. And so you can begin to go ahead and use this to build out more complicated applications that could either run on box, run off box. You can combine them together, and as far as the person calling it, there's no difference to you. And then conceptually, you end up with this. You end up with a bunch of applications with the work parallelized out where you don't have to go ahead and worry about it. So to go ahead and review what we talked at the top, we need something like temporal and spatial decoupling. So we want to make sure that we pass messages through a stream or a channel to a caller. We need spatial decoupling. Sorry, I screwed those up. So we need spatial decoupling, which is sending a message through a channel or a stream. We need temporal decoupling, which of course is like non-blocking APIs. We want that what we're sending across the network to actually be encoded in binary so it's efficient. And actually I should mention how much more efficient the binary is. So the encoding in RSocket, the frame encoding in binary, can do about 10 to 20 million encodes a second versus some of the faster stuff like JSON, you can do 30,000 a second. So it's not an insignificant difference when you switch to stuff like that. And then finally, you need some kind of application flow control, right? So the reason you want application flow control is when you move to a distributed system, as you begin to make network calls, your tail latency actually dominates the entire request. So the slowest request that you make ends up actually slowing down your whole application. And so using something like flow control, it actually evens out your latency and controls your tail latency, which actually makes your entire application faster. And that's the stuff that RSocket provides you for free, basically using it. And then Arsalan's going to go ahead and go over what this actually works or looks like in the real world.
Right. So it works in concept. So the question we asked ourselves was, we can build small test programs and show ourselves that we're millions of times faster than other things. But what happens if you build a real-world example? What does that look like? And so what we did was we applied it to the microservices problem because it's a distributed computing flavor du jour. And so what we're going to do is let's use a test that's out there. Some of you may have heard of it. It's called Acme Air. It's a bit of a test and a test harness that was built to test simulate real-world networked microservices infrastructures. Good news is IBM actually tests and publishes the test results on a specific system that's listed here on a regular basis. So what we said was, that's a good benchmark. Of course, IBM, inventors of Istio. How many people have heard of Istio? Okay. So this is what these days is known as a service mesh, Istio, Linkerd, a couple of others. And it's a REST-based, proxy-based networking scheme that people are trying to use for building their highly granular distributed microservices applications. So good. So we have this test that's published, and I'd like to point out a couple of things in this test. Now, these are not our numbers. These numbers are available online, published by IBM. So they ran the test, and the first thing I'd like to point out is they got up to around 60 users. And if you look at the throughput, you see that it's starting to level out. Right, the throughput chart there in the middle, which is telling us that we're reaching some sort of a capacity constraint there. So they were able to ramp it up to 60 users and did a pretty good job. They created a throughput of around 4.4K requests per minute, and then basically delivered the response time profile of 12 milliseconds. So 4.4K for 60 concurrent simulated users in a real application at 12 milliseconds, performance delivered, and that's where they started tapping out in this. And they run this regularly, so you can go and get the updated results anytime you want. So we said, okay, well, that's working on HTTP, REST, all the good stuff. Let's run this entire thing based on RSocket. And so we did. Oops. So stare at that for a second. Same test, same machine, same everything. We got to 60 users, delivered a throughput that was 4 times greater at a response time of a third of what they had. And not only that, we are still ramping in the throughput chart, so there's capacity available. So 4x the throughput in a real-world system at 1/3 the latency, just by using RSocket. So we got excited, very excited, and what we did, and by the way, there's a blog post that lays out all of this. It's listed there. So we said, okay, well, how far can we go? Same system, since we had more capacity. So we went to 300 users, got to 27, close to 30K, and look at the response time. And compare that to the 60-user response time. And then we just got crazy. We said, let's just go all the way. We turned it up to 11, got to 1,000 users on the same system, concurrent users. And the system kept churning, kept delivering more throughput, 37.8K. And you see the response time starting to spike. So the RSocket with all of the flow control built in, et cetera, all these things are acting together to start yielding a little bit on response time, but still generating more throughput in the system. And all we did was did the same test, except we did it on RSocket. So this was the moment, and this was when we realized that all the stuff that Robert just talked about, when applied in a realistic sense, can be, at least we think, pretty game-changing. So we invite you to sort of look at this, take a look at the blog post. You'll see what our methodology was. And also, if you're interested, we've got some good quick starts, so you guys can get started if you're not familiar with RSocket on our website. And that's pretty much it. I wanted to basically frame this in a real-world scenario, because sometimes it's hard to see what the basic theory is going to get you. And at this point, I think we're ready for questions. Robert, you want to come up here so to take the questions?
Wait.
So, so there are different components when you're making service-to-service calls, right? So how about service discovery and serialization and deserialization? Is that something part of the RSocket or?
Yeah, so there's the RSocket protocol, and then on top of that, we have like a routing and forwarding protocol that builds on top of what RSocket offers. But with it, you basically don't need separate service discovery, load balancing. We have built-in serialization, and then coming in like the Spring framework, this is on the Java side, there's built-in integration with serialization stuff into there, and then other languages as well have serialization built in. So basically what you do is you just set up the application, they point at each other, and then everything is taken care of.
I have a follow-up question on, so gRPC, I think gRPC has two components, the server side and then peer-to-peer communication also. So if gRPC peer-to-peer, is that similar to RStream, or how does it compare?
So one thing I didn't talk about, and there's other talks that talk about this, in RSocket, once you make a connection, both sides are co-equal, right? So there isn't really like a client and a server in RSocket. There's the person that made the connection, and that's it. So I can connect to you and then actually act like a server. And so, and in both directions, right? So on either side, you can actually set up clients and servers and exchange messages. And we have a protobuf serialization, if that's what you like. We're looking at GraphQL, and then there's more of the standard kind of more straight up message passing kind of stuff where you just send messages back and forth. So it's kind of like this nice layer with pluggable transports, which I also didn't talk about. So you can say, hey, I want this on WebSocket so it works in a browser. I want to use TCP. I have a shared memory driver based on some stuff Todd did. And then you can go ahead and like plug that stuff in and pick what you want, and then pick the API that you want to use to talk in your application.
So, I mean, just to summarize, there's no server or client distinction because it's a completely symmetric scheme. And so you don't have to worry about, I mean, we have some demos where we show an entire server class, demo running inside a browser in JavaScript that is being accessed by other browsers. So you can do those kind of things with this thing.
My question specifically is about how does it compare to gRPC?
In performance or in features?
Performance. We have a blog. It was real quick. Like we could do with 92 megs of RAM, we could do like 800,000 RPS, and they died.
So you'll see similar deltas, and we can point you to, I mean, if you visit our blog, similar deltas to this. In fact, better in many cases. We can
talk about it afterwards if someone has a question.
Thanks, guys. It was very interesting. And I'm sorry if this is a bit of a stupid question, but when you had the graph up with destination 1 and 2 and destination requests and says, you can send me 3 response packages, it's a bit of a two-part question. Is destination 1 dependent on getting all 3 packages, and what kind of retry methodology or mechanics do you have in?
That's a good question. So first off, it's kind of this request and semantics from Reactive Streams. So I send you 3, right? And that means you can send me 3 messages. You don't actually have to send them. I could even say, hey, send me 8. And that's kind of like these tokens you can use up. Once you use it up, then the rules say you can't send anything else. As far as retry semantics go, once a stream receives a terminal event like an exception, the stream's torn down, right? But because it's message passing, what you can do is you can intercept the exception and then not hand it back and then just do a retry, if that makes sense. And that's kind of built into the frameworks around it, so it's not something you do yourself. You just basically do dot retry.
Thank you. This seems somewhat reminiscent of nats.io, and I'm wondering if you're familiar with that and could sort of maybe draw some distinctions. So, because I'm more familiar with that. Yeah.
So Nats is probably more like a message broker, like a protocol for a message broker. And one thing they did that some people like that maybe I don't like as much is that it's string-based. So it's a very simple text protocol, so it's easy to understand and maybe debug. But then you get this trade-off with having things encoded in string. And it's actually really significant to do that. Like, you can end up basically making all your work like JSON and text. I had a joke with a guy at work. We'd be like, if you just stopped any box randomly at Amazon, it's like 99 times out of 100, and you go look at it, they will be parsing text, right? And so, I mean, you're basically like burning money. The other thing I said, if you care about the environment, you shouldn't use text. So that's like a huge difference. Because basically it's, I mean, it's very inefficient to do that. And that's one of the big things. And then the different interaction models, and the final thing is the pluggable transport piece, right? So when we built RSocket, we wanted to make it so that you could like pick a transport that was appropriate for your use case, right? So sometimes it's WebSockets, sometimes that's shared memory, sometimes it's TCP. And we wanted to future-proof it so something like Quick comes out, you don't actually have to change your APIs. You just say, hey, I'm going to use Quick, and that's it.
So Robert briefly mentioned the various interaction patterns that you can have. So we have in RSocket, well, if you just look at REST and HTTP, you've got a request response, right? That's it. In RSocket, first class interaction can be request response, fire and forget, channel, or a bidirectional channel. So right, stream and channel. So these are all first class primitives of the protocol. So a lot of the work that people do with buffering and you know, queues, etc., are actually handled straight away inside the network protocol itself. So that's something we didn't get to spend time on, but if you're interested, you should probably take a look at it. You'll find that very interesting. Was there a question on that side? Here.
Being that you're using persistent connections, how do you deal with load balancing? That's a good question.
Persistent connections with load balancing. You want to take it?
Yeah. So when you connect, you get an RSocket object, right? And then what we do is we actually collect those RSocket objects together and, well, I mean, frankly, just load balance across the connections, right? So you have like these like 12 different, are you talking about like application load balancing, or you want to go ahead and like load balance and quiesce and move them between?
Pod level, like if you say you're in Kubernetes, you've got 3 pods that all do the same thing, and they're communicating with 2 other pods that do something else.
It's like an ELB style.
Yeah, if you have one pod that goes down and is replaced,
Okay.
How do you not overload the one pod that?
This is actually something we do that is pretty cool. Because there's back pressure and this availability metric, we can actually look and see like how much load you can handle. We also take a look at the latency that you have, and then we actually predict the latency. So if you're not within a window, we can slow you down and speed you up. So we get this bucket of persistent connections come in. We actually use a flyweight for the load balancer. Put it over the bucket of things you want to talk to, and then pull 2 at random, and then actually go ahead and find the best candidate and send it. So if one of them goes down, very quickly it like moves them off and goes ahead and sends it to somebody else. And here's the other cool thing. Because there's this idea of back pressure, if someone's down, they're not actually sending you like a request end to send you more data. So you'll actually just stop getting having traffic sent to them too.
Do you then also do takeover? So if you did have one node that did go down but was actively trying to communicate or process some sort of work with another service?
Yeah, so there's this concept in the protocol called resumption. So if you have a flappy connection, something goes down, what it does is it actually makes it seem like a stable persisted connection. So connection flaps, kind of buffer stuff on either side, someone will pick it up and fill in where you left off. And so that's how you would do something like that.
And resumability can be both warm and cold. So, mobile use cases, unreliable networks, connections, it's a natural to use RSocket. Any other questions?
Thank you. Some of the things, they require eventing, right? Like how does RSocket have anything to support eventing, or it's completely different?
Do you mean like event sourcing or?
Yeah.
I've been asked this before. We haven't built anything right now, but it would be very natural. So another thing we didn't talk about is this connection oriented. So when I connect to you, right, all the streams that I have come on that same channel. So you could begin to go ahead and save them. And you could maybe make the case that resumption could be kind of a form of event sourcing too. So you might not need to use it quite the same way. So you could probably use resumption as a fill-in for event sourcing in some use cases, I think. Because,
And it's important to understand that we're not advocating for death to all event queues. We're not saying that. I mean, there's a natural use case for events. Maybe your application requires a queue. Then use the queue. It's there. We're also not advocating that you throw out all of your MQ and your Kafkas because now you can actually do. Where RSocket becomes very useful is when you are using those mechanisms. You may be using Rabbit, or you may be using Kafka because you have a bidirectional streaming interaction, and there's no such facility in REST or HTTP. So you basically use something that was designed to ingest today and consume tomorrow as to do your bidirectional streaming. So it's those cases that tend to introduce a lot of infrastructure in your applications. So there's a place for queues, there's a place for Kafkas of the world and the Rabbits of the world, and even HTTP. I mean, it was designed to schlep documents. It's great, but the important thing is that oftentimes you end up being forced in a place where you're using some of these architectural elements, these infrastructure elements, unnaturally, because you have no other options. And that's where a massive amount of performance degradation, et cetera, comes in. So for example, if you just take the example of these service mesh thinking that's going on these days. What is a service mesh? What is the problem it's trying to solve, and how is it solving it? A service mesh is basically a response to the fact that I have two services sitting apart from each other, and they need to be able to talk to each other in a secure, controlled fashion. Right? So the response is, let's put a sidecar there, which is a reverse proxy. Let's put more proxies there. Let's introduce service infrastructure, discovery infrastructure, all of that stuff. Build all this apparatus of layers upon layers so that service A can talk to service B. Well, we have a model for this. It's called networking. That's how you talk, one service talks to another service, not proxy upon proxy upon proxy. So it's, now is that saying that you can't ever use REST or you should never use a service script? No, that's not what we're saying. But the question is, when you're trying to build a performant, simple to deploy and use system, do you have options other than building those big scaffolding around your services? And that's one of the ways you use this. Hopefully that gets to the heart of what you were saying.
Thank you.
Yeah. You have another question?
More questions?
How does the contract between two different services look like? Do you do code generation, or do you use a proxy?
Contract, the IDL, RPC, as well as the messaging.
Yeah, there's two ways. You can do, like I said, message passing between both of them, which is more akin to REST. You just send it. Like, so Spring has like this concept they're building in, we're building into other stuff like a named stream. You can do IDLs, so protobuf, GraphQL, stuff like that. So again, like you said, you can bring your own API, so you can pick what is appropriate for the use case that you're doing.
And strong contracts are always good if your application can have them, right?
Yeah.
So we do provide the RPC abstraction and the IDL abstraction. All right.
Any other questions?
Guess we're done.
All right. Thank you very much.
Yeah, thank you guys.
very much. Appreciate it.